Here we're going to develop the idea of spontaneity. We've talked a little bit about spontaneity before, and here we're going to put it on a more firm foundation. The two examples we used, or two of the examples we use for a spontaneous process, is suppose we have two metal blocks, and this is high temperature and low temperature. What we find is that a spontaneous process occurs, heat flows from the high temperature to the low temperature block. This is a process that happens spontaneously. There's no urging, it just happens. A second example we used in class was a case where we had two gases, argon and helium, same pressure, same temperature, and they were separated by a partition. If we now remove this partition, what we find is that argon distributes evenly and helium distributes evenly in this volume. That happens spontaneously. It just happens. And in fact, we never see the reverse happening. We never see argon collecting over on one side and helium collecting on the other side. Just as we never see heat being transferred from the low temperature to the high temperature. It's always one way. It's spontaneous. It just happens without any urging. And the colloquial expression, shit happens. Oh, I probably shouldn't say that, so let me go back and bleep that out. What we have from our discussion of the second law is things happen spontaneously if the entropy change in the universe during that process is greater than zero. That's the definition of a spontaneous process. You start someplace and then you end someplace else. And if the entropy of the universe in that second place, that final state you end up with, increased, then going from the initial to final state was a spontaneous process. Now let's look at this. This says that the entropy change at constant internal energy and volume is greater than zero for a spontaneous change. Let's just see that. Okay, this is for an isolated system. Let's take, for example, the isolated system of the universe. This is the universe, which is isolated. That is our assumption. Isolated means that Q is equal to zero. You cannot transfer heat. That's the definition of an isolated system. W is equal to zero. You cannot do any work on the surroundings. The surroundings can't do any work on the system. That's an isolated system. And therefore du, which is dq plus dw, is zero. Let me just make infinitesimal changes here, dq and dw. And we said for an isolated system, delta S is greater than zero for this whole system in here, and it's isolated. What this means, let's assume we have PV work only. So this is minus P dV, PV work only. So that's the only kind of work, so that's minus P dV. And U is a constant, and V is a constant. So this implies for an isolated system, the change in entropy at constant U, which is 0, du is 0, and constant volume, dV is 0, no volume change here, constant volume is greater than 0. So there it is. For an isolated system, ds at constant internal energy and volume is greater than 0. So you might sort of notice we've sort of subtly switched from the entropy of the universe to the entropy of the system. And so that's what we're going to do for the next few equations, is focus on the system. So this is an isolated system. The entropy change in an isolated system where you have constant U and V is greater than 0. So this is the criterion for spontaneity for an isolated system. Now what we're going to do is to make some other conditions here for constant volume and entropy, constant pressure and constant entropy, and so on.